In this problem, we're told in 1865, Jules Verne proposed sending men to the moon by firing a space capsule from a 220-meter-long cannon with a final speed of 10.97 kilometers per second. What would have been the unrealistically large acceleration experienced by the space travelers during their launch? So let's go ahead and solve this problem. So if we can just imagine it here, imagine we have a cannon, right? So here's our cannon, and imagine it's just going to be firing, right? We're firing some astronauts into space, okay? So just get an idea of what's going on. So the way we solve these problems are by using kinematic equations, which are these equations here on the right, okay? And so what we want to do first is look at these equations, and then we're going to write down every single variable, and then we're going to see whether or not we have it. That's the first thing you always want to do. So let's write down our given, right? So write down every single one of these variables. So in these problems, it says delta x, but keep in mind what delta x is. It's just the change in the x position, but in this problem, we're going upwards, right? So generally you can say delta y, but really it's still your change in position in whatever direction you're traveling. So I'm just going to write delta y, but just keep in mind that's it's going upwards. That's the reason I'm doing that. So we have delta y, we have v sub 0, we have a, and we have t. So these are the 5 variables. So let's determine whether or not we're giving them. So let's think about this problem, right? So we have this cannon, right? So the cannon is like 220 meters long. So I'm actually just going to redraw it, okay? So here's our cannon, okay? And so we know it's 220 meters long. In the beginning of the cannon, right? This is where they are in the beginning. Think about what they're doing. They're just at rest, right? They're not moving at all. So essentially, since they're not moving, what is their velocity? So right here in the beginning, their velocity is going to be 0. And so we call this initial velocity because it's the initial part of whatever's going on. So we just say v sub 0 is equal to what? Well, it's 0 meters per second because they're not moving. Okay, think about what happens at the end of the cannon. They tell us with a final speed of this, right? With a final speed of this, meaning at the end of the cannon, right here, their velocity is going to be what? Well, they tell us 10.97 kilometers per second, right? So they're going to start here. Some reaction is going to happen to propel them forward, and before they leave the cannon of this 220 meter long cannon, they're going to be traveling at this speed, right? So these are the variables we're given. We don't know how long it's going to take, and we also don't know their acceleration, right? Because that's what we're trying to solve for, right? We're trying to solve for the acceleration. So let's just write down the variables, right? So this is actually upwards. I just drew it sideways, but just keep in mind it's upwards. So what is their change in y? Well, over this time period, their change in y is going to be what? From the beginning to the end is 220 meters. So their change in y is 220 meters. So what about v? So we labeled these already, v and v sub 0. V is just your final velocity. V sub 0 is your initial. So initially their velocity is 0 meters per second. And then finally their velocity is 10.97 meters per second. So, or not meters per second, kilometers per second, sorry. So what about their acceleration? We don't know, and that's what we're solving for. So I just put question mark, and then t, we also don't know, but we're not going to be solving for a t, so I'm just going to put question mark still though. But just keep in mind we're trying to find a. So when we solve these problems, the first thing you have to do, right, so we have all the variables, okay? Let's determine which equation we want to use. So think about the equations, right? Look on the right. The ones that say delta x, just imagine they're delta y. It's interchangeable. And so think about what we don't have. We don't have the variable t. So the equations here that contain t, we're not going to use. Okay, so if you look 1, 2, and 3 all contain t. So we're not going to use those. But if you look at the fourth one, we have v sub 0, and we have delta y, right? So what we can do is go ahead and solve for a, because that's the only variable left. So we know which equation we're going to be using. We're using this one. And so when we do this, we have to make sure that our units line up. So this is 10.97 kilometers per second. And notice this is in, generally, you solve these in meters, so I always write if it's 0 in meters per second. And notice this is in meters too. So we want this to be in meters, right? So we got to convert from kilometers per second to meters per second. So 10.97 kilometers per second. We know that there's going to be 1,000 meters for every 1 kilometer, okay? And so what you can do, right, if I write it like this, essentially just multiply by 1,000, the kilometers cancel, and you get it in the correct units, right? So you just want to do 10.97 times 1,000, and that's going to give you your correct units. So just do 10.97 times 1,000. So yeah, you're going to get 10,970, and then it's in meters over seconds. So cool. Now we have all the units lined up, right? So this is that. So we have all the units lined up, and we can just plug it in. So this is the equation we're using. V squared equals v sub 0 squared plus 2a times delta y in this case. So let's just go ahead and solve, right? So plug in the variables. V, we know, is what we just solved for. 10,970 squared is equal to v sub 0 squared, which we know is 0, right? 0 squared is still 0. So I'm not going to include it, right? So it's just going to be 2 times a times delta y. What's delta y? So delta y is the change in the y, which is 220, right? So 2 times 220 is just 440. So this is going to be 440a. So what we're going to want to do, right, is just go ahead and divide both sides by 440, and that's going to give us a. So just do 10,970 squared, and then you're going to want to go ahead and divide that by 440. So when you do this, you're going to get a pretty big number. It's going to be equal to, a is going to be equal to 273,502.0455. Yeah, so this right here is going to be your answer, right? So you can round this if you want. Just make sure you do what your teacher wants. I'm just going to leave it in the exact value. But if your teacher wants it in scientific notation, or they want it in just a more rounded value, just make sure you go ahead and do that. But yeah, so keep in mind the units though too. So this is going to be in meters over second squared. So meters per second squared, right? That's what you measure acceleration in. So this right here is going to be your answer. Once again, rounded if you want the more exact, or less exact, sorry, or put in scientific notation if you want. But yeah, so meters per second squared, this is your acceleration. And yeah, hopefully you found this useful.